Okay, so ensembles always have the spread, and we talked about the ensemble mean, ensemble error, standard deviation, and how closely bunched together the ensemble members are, and how that corresponds to skill, and so on and so forth. But ultimately, if in this probabilistic forecasting method of ensemble approach, has to also represent model uncertainties. And here are the four main approaches that are followed in ensemble prediction to represent model uncertainties. A multi-model approach in which different models are used in each ensemble members. Models can differ entirely or only in some components, for example in the convection scheme. In some sense, the models have a common heritage going back to the development at, let's say, GFDL and NCAR, just as an example. And then they have various evolutions depending on whether it's in Europe or in the tropics or in Russia and China and so on and so forth. But the convective parameterization, which is mentioned here, is something that is always been dependent on data. So it depends on whether the method, the parameterization, evolved for data from the middle of the continent or in the ocean, and so on and so forth. So those typically tend to be different in models. And if you can do perturbations of initial conditions and produce multiple ensembles with the same models, you can also treat each different model for the same period or for the same process, like 2-meter temperature anomaly prediction, as ensemble members. So that's the multi-model ensembling approach. And generally speaking, to first order, you can think of them as presenting flow-dependent errors in a way that they get smoothed out when you do multi-model average and multi-model ensembling. So there is clear indication that there's a benefit to doing ensembling and then multi-model ensembling as well. A perturbed parameter approach in which all ensemble integrations are made with the same model but with different parameters defining the settings of the model components. This is done in the Canadian ensemble system, for example. A perturbed tendency approach in which stochastic schemes designed to simulate the random model error component are used to simulate the fact that tendencies are known only approximately. So when we measure all these data we looked at, for example, satellites, ships, radiosondes, airplanes, whatever, moorings in the ocean, they give you discrete data, but the growth rates are not always easily measured. You can derive them from discrete observations. So the idea here is the tendencies are not known very accurately. So the model has different tendencies, for example, than the observations. Then even if you get perfect initial conditions, forecasts are going to be off or have errors. So that's the approach here. I think this was initially started by Tim Palmer at ECMWF. A very smart guy, one of the smartest in the business, so anything he says you have to pay attention. So this is one example, ACMWF stochastically perturbed parameterization tendency scheme, stochastically perturbed parameterization, SPPT. Stochastic backscatter approach in which a stochastic kinetic energy backscatter SKEB scheme is used to simulate processes that models cannot resolve. For example, upscale energy transfer from the scales below the model resolution to the resolved scales. Another example is a SKEB scheme used in the ECMWF's ensemble prediction system. So models have a certain grid scale which is based on being efficient for computational purposes, and numerical weather prediction models have a higher resolution because they integrate shorter periods. Climate models have a lower resolution because they integrate for many seasons, and climate projection models will have even lower resolution because they integrate for multiple decades or even centuries. And there are processes. Remember when we looked at the initial podcast, we said any quantity can be represented as the seasonal mean plus the subseasonal part and the synoptic part. And in the real world, when you do kinetic energy and other potential to kinetic energy conversions and so on, you see that there are often upscale energy transfers from synoptic scales to the subseasonal scales, and subseasonal scales can rectify seasonal means and so on. These cascades are not represented fully in models that don't resolve those scales. So this is where it becomes important to think about seamless prediction systems, which can do all the spatial scales, but obviously that has many other issues in terms of initializing and resolution and so on. Okay, so here are the key characteristics of the 9 TIGI operational global medium range ensembles. We are jumping into ensembling already now, going from characterizing errors, but we will come back to it. So TIGI, of course, again is Thorpek's interactive grand global experiment on grand global ensemble. Here are the centers again from Australia, China, Brazil, Europe, Japan, Korea, Canada, and US. Initial uncertainty method. Okay, so we are talking still about uncertainty estimations and depictions. Singular vector for southern and northern hemisphere, bread vectors, EOFs, and combinations of things, local ensemble transform Kalman filters, ensemble transform Kalman filters. So these are ways in which observational information is included locally, and remote observational impacts and so on and so forth. Okay, without going into details, model uncertainty, is it depicted? No. Here some of them do that, okay, explicitly. Truncation, so spectral models often call it truncation, how many waves you choose to represent. That corresponds to a grid resolution, of course. So TL 119, so corresponds to 1.5 degrees and 210 kilometer spacing. T2 133, and so on and so forth. So again, uncertainties are represented here. This is the vertical levels. Forecast lengths in terms of days also varies. Number of members, perturbed and unperturbed ensemble members, also vary. So you can see CMWF is kind of the global leader on innovation and ensembling and resolutions and skill scores and in general reliability. They are the kind of tend to be the gold standard. Okay, so number of runs per day based on the UTC also differs. Okay, so these are the initial uncertainty method, model uncertainty simulation, truncation and approximate horizontal resolution, number of vertical levels, and so on. And this is when you do grand global ensemble, you are mixing these various configurations and approaches, and there is an attempt to make them kind of stick to a same protocol whenever you do multi-model activities like IPCC or S2S forecasts as multi-model ensembles, or even individual models presenting their forecasts. There have to be protocols. So each TIGI ensemble member is defined by the numerical integration of the model equations adopted by the production center in question to simulate the Earth system. In other words, each single T-hour forecast starting at day D is given by the time integration of a set of model equations from initial time 0 to time t. So here is the error starting at day D integrated for time t. So it has some error in the beginning, and this is integrated from 0 to t of this quantity here, AJT plus PJT plus dPJT, where time is of course t is of course time. AJ is the tendency due to adiabatic processes like advection, Coriolis force, pressure gradient force, and so on. Pj is the tendency due to parameterized physical processes like convection, radiation, and turbulence. Because each model is different, you can divide the tendencies into those components. And dPj represents the tendency due to stochastic model errors and unresolved processes. Okay, and the book goes into details of how each model does these tracking in the for the TIGI, but I'm not going to go into the details of each model here. So let me leave this podcast here and come back to operational ensembles of an S2S monthly forecasts and reforecasts of S2S monthly operational ensembles in the next podcast. Okay, so the main point is that there is a systematic and quantitative effort to represent model uncertainties, including stochastic error growths in the models due to unrepresented processes and so on. Okay, so this is very important, and models do worry about it a lot.